Hello everyone. The title of this video is Add and Subtract Rational Expressions or Fractions with a Common Denominator. So in this video I'm going to be going over 16 examples in which we're given two fractions, two rational expressions, and we're asked to either add those fractions together or subtract those fractions. And in every single example in this video, it's already nicely set up. Because if you recall, in order to add or subtract fractions, first you need to get a common denominator. You need the denominator of both fractions to be the same. And in every single one of these examples in this video, they are already the same denominator. Okay, so before I get into actually writing out the examples here, every single example I'm going to do in this video is taken directly from a free online textbook at openstacks.org, and it's their Intermediate Algebra 2nd edition book. I am in section 7.2 titled Add and Subtract Rational Expressions. And in this video I'll be doing exercises under the heading Add and Subtract Rational Expressions with a Common Denominator. And I'll be working on exercises 75 through 90. 75 through 90. That's, again, 16 examples. So example 1 in my video will correspond to exercise 75, example 2 to number 76, etc., right, all the way down to example 16 being exercise 90. And I will have timestamps for each of the 16 examples in the description of the video below. So if you'd like to see any particular exercise, say you wanted to see me work out exercise 83 here, well, that would be example 9. Alright, so you click on example 9's timestamp and you can see me work on exercise 83, and so on, right? You just bounce around if you don't want to watch them all. And one thing I like to try to remember to say also before I work on the problems is when I bring up a new example in the video, pause the video and try to work out the problem yourself before you see me doing it. Because if you're just watching me do it and not working on anything yourself, what good is it? You're not going to learn anything. Alright, so pause, try to work it out yourself first, and then watch me do the problem and see, how you did. Compare and contrast your work with my work and see how far along you are with the material or how well you're grasping it. Alright, so we'll start with exercise 75. Now in the first 8 examples we are asked to add fractions with the same denominator, with a common denominator. And in the last 8 examples we're subtracting fractions with the same denominator, right, or with a common denominator. And just remember that subtraction is really addition of the opposite, right? When you subtract, you're really just adding a negative or adding the opposite. Just keep that in mind. Alright, so example 1, which again corresponds to exercise 75. I have, and for again examples 1 through 8, I'm asked to add the fractions that already have a common denominator, and of course simplify the fraction. Now I'm assuming you've already read through the section on simplifying fractions. That's section 7.1 of the OpenStax Intermediate Algebra 2nd edition book. I've also put out a video previously where I go through simplifying rational expressions, so I'm assuming you know how to do that already. Alright, so first example we have 2/15 plus 7/15. Notice that both fractions, alright, and like I said earlier, this is going to be the case for every example in this video. Both fractions have the same denominator, or what they call a common denominator. Alright, and that is needed in order to be able to add or subtract fractions. Not multiply or divide. Right? You don't need a common denominator to multiply or divide fractions. You only need a common denominator, right, to add or subtract, which we are doing here in this video. Alright, so very simple enough. And I'll write the rule over here. Right, when you're adding fractions, say I have a fraction, a over c plus another fraction, b over c, and you see they have the same denominator of c. When you put them together, that common denominator stays as the denominator. Right? You don't add them together. So the denominator of the sum, right, the final result, is still c. Right, the same denominator throughout. It's the numerators that you combine. The numerator of the sum will be a plus b, the first numerator, plus the second numerator. Alright, and there you go. Alright, so keep this rule in mind as we go through. So here I have, again, 2/15 plus 7/15. They both have the denominator of 15. So that's going to be the denominator of the sum. So let's write 15 in the denominator again. And then you're just combining the numerators. The numerator would be 2 plus 7. First numerator plus second numerator. And you know what 2 plus 7 is, right? 2 plus 7 is 9. So we end up with 9/15. Alright, then after adding, simplify. So right there here. Same thing with subtraction, right? So after adding, simplify. Now hopefully you recall, again, I'm assuming you recall how to simplify fractions, simplify rational expressions. So here comes the simplification part. It's where you factor the numerator and denominator completely. Right? So one other thing I'm going to be assuming is that you know how to factor polynomials. And if you don't, you might want to refresh your memory. A good place to do that would be in Chapter 6 of the OpenStax Intermediate Algebra 2nd edition book. Chapter 6, every section of that chapter is about factoring polynomials, different methods for factoring. Difference of squares, sum of cubes, difference of cubes, the AC method for quadratic trinomials, factoring by grouping, all that stuff. Alright, so again, I'm assuming a lot here, that you know how to factor polynomials and then use the factoring techniques to help you simplify fractions. But remember how to simplify fractions. You factor the numerator completely, which would just be 3 times 3, right? That's 9. Factor the denominator, or you could write 3 squared, right? I'll use powers later. And then 15 factored completely is 3 times 5, right? And then you cancel, right, any common factors that the numerator and denominator might have. So I'm noticing they both have this common factor here of 3. So when you cancel common factors, technically they become the number 1, right? Because anything divided by itself is 1. So what I'm left with here is 1 times 3/5. So 3/5. And there we have it. Right? This is the final result. Okay. And you should check your solutions, test your answers out. Now, when everything's a number, you could pretty easily, if you don't believe that this is equal to this, put up a calculator. Now I know this might be pretty tiny here, but let's take 2/15, right? 2 divided by 15 plus, and then 7/15, 7 divided by 15. See what we get. See, we get 0.6, 0.6. Now let's take the expression we ended with, 3/5, right? 3 divided by 5, and I get the same exact value, 0.6 again. So this value I ended with, 3/5, is equal to 2/15 plus 7/15, right? And that's a way to check your results. You can use a calculator if you want. It doesn't bother me any. Right? Just to make sure that the expression in the beginning has the exact same value as the expression in the end. Okay. Alright, so I'm going to keep doing this. Alright, now the next example, again, just has numbers. 7/24 plus 11/24. Once again, the denominators are the same, so I can jump right to the addition. Now the fraction you'll end up with will also have the same denominator. Remember this rule again, right? When adding or subtracting, that common denominator, right, stays throughout. And I just combine the numerators. So the numerator of the sum is 7 plus 11. Now 7 plus 11 is 18. Alright, so we end up with 18/24, which is totally fine, but as I mentioned in the previous example, and we're going to do this with every example, after I'm done adding, then we're going to simplify the fraction if possible, right? See if we can find any common factors in the numerator and denominator. So 18 is 2 times 3 times 3, right? 2 times 9. Or you could write 2 times 3 squared, same thing. And then 24 is 8 times 3, and 8 is 2 cubed, right? So 2 times 2 times 2 times 3. That's 24 factored completely. And then I'm canceling, right, common factors in the numerator and denominator. Well, I see a 2 up here, a factor of 2 down here, so those will become 1. See a factor of 3 in the numerator and a factor of 3 in the denominator. Those will become 1. And so now all I'm left with in the numerator is 1 times 3, so 3. And in the denominator, I'm left with 1 times 1, and then there's still 2 times 2 down here. Now 2 times 2 is 4. And that's as simple as this gets, right? 3/4. Alright, and then one more time. Alright, one more time here. I'll check my solution with the calculator. Again, you don't have to have a graphing calculator to do this. Any calculator should be fine. But I take 7 divided by 24, right? 7/24, plus 11/24, right? 11 divided by 24. And I'm getting 0.75. 0.75. And look at the final result. 3 divided by 4, 3/4, that is also 0.75. They are indeed the same value. So we must have done everything correctly. Okay, wonderful. So yeah, so in every example of this video, we're going to be adding or subtracting. All right, and I'll just write in the minus sign here, because no matter if it's adding or subtracting, you're doing the same thing. If they have a common denominator already, that's going to be the denominator of the resulting sum or difference. And then you just take the first numerator plus the second numerator, and that'll be the new numerator. And for subtraction, you take the first numerator minus the second numerator, and that'll be the new numerator. And then after adding, after subtracting, then we're going to simplify, meaning factor the numerator, factor the denominator completely, and then cancel, right, any common factors that the numerator and denominator have. And of course we'll check our solutions, right, test it out at the end. All right, next example. So now we're getting into examples where there are variables, polynomials with variables. So when I'm done, as you've seen me do in other videos, after I'm done, I'm also going to write out the values that make the expression undefined. All right, remember, you don't want a denominator to be 0. Can't divide by 0. All right, that's undefined. That's bad. So when I'm done writing out the final result, I'll go back and look at the denominators throughout the problem and see what are values that I can't use for the variables. All right, what makes a denominator 0 anywhere throughout the problem. All right. Okay, so again here, first fraction, 3 times this variable c divided by, and then the denominator for this fraction is 4c minus 5 plus next fraction 5 divided by 4c minus 5. Alright, so just like the previous two examples, these two fractions already have the same denominator. So when I add them, that will be the denominator of the final result, 4c minus 5. The numerator is just the combination of the numerators of the two fractions. The first numerator, 3c, plus, and then the second numerator is 5. Now, you try simplifying, but both of these polynomials can't be factored any further. So this is as simple as it gets, right? Because they're both as factored as they can be, and I'm not seeing any common factors. And be careful, right? Some people will cancel the 5s or cancel the c's. Remember, you can't cancel common terms. You must factor first. Right? Don't do that bad canceling. All right, then off to the side here, looking at all the denominators throughout, well, the only denominator that shows up is 4c minus 5. The only factor in the denominator that shows up is 4c minus 5. Remember this, that can't be 0. So that means that the value of c cannot be 5/4. And I'll just make a note of that as well. So the value of this expression that I started with this addition is exactly the same as this value for any value of c except 5/4. Right? If you replace c with 5/4, you'd have denominators of 0 somewhere, and that's not good. That's undefined. So let's test this. Right? When you're done with a problem and you think you're done, test it out. Try to plug in some values of c and see if you get the same result. See if the original sum is exactly the same value as the final result. And they should be. Right? If you did everything right, they should be the same value. How about if c were 0? Well, then the original expression, and I'll do this, here's the value of the original expression, and here's the value of the final expression. And hopefully they're the same, and they better be. Well, if c were 0, we'd have 0 divided by -5, so that'd just be 0, plus 5 divided by -5 would be -1. 0 plus -1. The original expression would have a value of -1. The final expression would be 5 in the numerator, -5 in the denominator. 5 divided by -5 is -1. Great, they are the same. They are equal when c is 0. And it should be the case, right? The beginning expression should be exactly the same value as the final expression for every allowable value of the variables. So every value except 5/4. So let me just do one more. How about if c were, 1? Well, you'd have 3 divided by 4 minus 5. 4 minus 5 is -1. 3 divided by -1 is -3. Plus, and then -5, you'd have -8 for the value of the original sum. And now I'm hoping that that's the same value I'm going to get at the end here. Well, when c is 1, 3 times 1 is 3, plus 5 is 8. I have 8 in the numerator, and then 4 minus 5, -1 in the denominator. 8 divided by -1 is -8. And they are equal. And you can try that out with any values you want, right? Just to convince yourself that these are indeed the same expression. The original expression and my final expression are equal. So I can plug in any value of the variable I wish, right, except for 5/4, and the beginning value should be the same as the end value. You can check that out, and I leave it to you to check more if you want. Obviously, you can't check every possible number, but I would suggest doing at least a couple, just to see that they are the same for at least a couple values. That way you can convince yourself that you didn't make any mistakes. All right, and I'll do this once more with number 4 as well. Then after that, after example 4, I'll just tell you, plug in values and make sure they're the same. All right, so number 4, example 4, you have 7 times m divided by 2m plus n plus, and then another fraction, 4 divided by 2m plus n. Notice they already have the same denominator, right? 2m plus n. So when adding, right, that's going to be the denominator of the final result then, right? That common denominator, 2m plus n. And I combine the numerators, right? The numerator of the sum will be 7m plus 4. Right? 7m plus 4. And the numerator is already as factored. You can't factor it any further. Same thing with the denominator. So this won't simplify any further. Just like example 3, that's as simple as it gets. All right, then off to the side here, I'm going to write out some conditions on the variables. Right, like in example 3, c couldn't be 5/4 because it'll make me divide by 0. All right, I'm looking for what makes a denominator 0. Well, the only denominator showing up throughout this problem is 2m plus n. Right, so that tells me that 2m plus n can't be 0. Or, if you solve for n here, n, the value of n cannot be -2 times the value of m, kind of subtracting 2m here. All right, so there's a condition on the variables. So what that tells me is, if I replaced m with 1, I couldn't replace n with -2. If I replaced m with 3, I couldn't replace n with -6. If I replace m with 0, I can't replace n with 0, and so on. Right? As long as n is not -2m, you're fine. But if n is -2 times m, then you'll be dividing by 0, and that's bad. So again, let's test this. Let's test our result here. Again, this is a pretty simple one. You just add, and there was no simplification to do. But here, this is an expression with 2 variables. So I'll do here's the original expression's value, and then the final expression's value. And now, what if m were 1 and n were 0? And that's fine. You can do that. That doesn't satisfy this. When m is 1, n can't be -2. That's the only value. So when m is 1, I can replace n with anything but -2. So m equals 1, n equals 0. That's fine. Let's see. The original expression, I'd have 7 halves plus the next expression would be 4 halves. That'd be 11 halves. The value of the original expression would be 7 halves plus 4 halves, or 11 halves. The final expression, if m is 1 and n is 0, you'd have 7 plus 4, 11 in the numerator, 2 plus 0, 2 in the denominator. You also would have 11 halves, and they're equal, which is great. That's what I want. And that should be happening, right? No matter what I plug in for m and n, as long as n is not -2 times m, whatever I plug in for m and n, the value of the original sum should be exactly the same as the value of the final expression. So I'll do one more of these. How about if m were, 3 and say n were -1, whatever. Right? Again, if m were 3, the only value I couldn't use for n would be -6. I can use anything else, so I'm using -1 here for n. Let's see, the value of the original expression. You'd have 21 over 5. So 21 fifths plus 4 fifths would be 25 fifths, or 5, for the original expression. The final expression, if m were 3, that'd be, again, 25 in the numerator. And then if m were 3 and n were -1, you'd have 6 minus 1, 6 plus -1, 5. 25 in the numerator, 5 in the denominator, you get 5 again. 5 equals 5. And I leave it to you. I would leave it to you to try some other values. Right? Try some other values for m and n, and you will see that the original expression has the same exact value as the final one. And it should, as long as you're not dividing by 0, right? As long as there's never a denominator of 0. Okay. Alright, so now, continuing on, right? We still have adding fractions with the same denominator. So example 5, these two fractions again already have the same denominator. So that's going to stay the denominator of the sum. So 2r minus 1 there. And then I'm just adding the numerators. We have 2r squared, the first numerator, plus, and then the entire second numerator, but no, let's just write it again, 15r minus 8. So that's all in the new numerator. So now I've added. Now we try to simplify. All right. Now in the previous two examples, once I added, there was no more simplification to do. The numerator and denominator were totally factored already. But here, the numerator can be factored further. And again, I'm assuming you know how to factor quadratic polynomials. So this 2r squared plus 15r minus 8, that factors to, there would be a 2r, and you can do guessing and checking, you can do the AC method. Again, go back to chapter 6 and refresh your memory on factoring. Yeah, you'd have to have a plus 8 here and a minus 1 here, right? That'll give me the plus 16r minus 1r for the plus 15r. And then you have the 2r minus 1 in the denominator. And I hope you can see the common factor. Right? See how the numerator has a factor of 2r minus 1, and the entire denominator is just the factor 2r minus 1. So they both have 2r minus 1. And then all I'm left with is r plus 8 in the numerator and 1 in the denominator, but there's no need to write divided by 1. Right. So the value of this sum is going to be whatever r is plus 8, whatever you choose for r, as long as you don't use certain values for r, though. Right. So off to the side, r cannot be a half. Right, because if I replace r with a half, the denominators, right, would be 0 throughout this problem. You can't have a denominator of 0. But if you want, right, replace r with any number but a half. If you replace r with any other number, the value of this sum in the beginning should be exactly the same as the value of r plus 8. Right, so if check it out, if I replaced r with 0, the value of this sum here would be the same as 0 plus 8, or 8. You should get 8 here, 8 there. If r were 1, the value of r plus 8 would be 9, which should be the same as the value of the original. And again, I leave it to you to check some values for r and test to see if these two expressions are indeed equal. Okay. Example 6, pretty similar. Again, a nice easy setup here where we're adding two fractions and those fractions have the same denominator already. So when I add them, that common denominator, right, is the denominator of the sum, 3s minus 2. And then you combine the numerators. That's the first numerator, 3s squared, plus the second numerator, the 13s minus 10. Right, and again, no need for parentheses there because you're adding. You'll see we'll need the parentheses when we subtract the entire numerator. Okay, again, all great. I've done the addition, but now simplify. The numerator, 3s squared plus 13s minus 10, this can be factored. You just have to have a 3s in one of the factors and an s in the other one. And we have 3s minus 2 in the denominator. Let's see, we got negative 30. That'd be 15 and 2. So I need a positive 5 here, negative 2 here. All right, that'll give me the positive 15s and the minus 2s for the positive 13s. Great, and now hopefully again you're seeing the common factor in the numerator and denominator, right? The 3s minus 2 is common to both the numerator and denominator. So those divide to be 1. And all I'm left with is s plus 5 in the numerator and 1 in the denominator. So just s plus 5. And then once again, off to the side, I'm going to put down conditions on the variables. The value I replace s with can't be 2/3. Right? Because if s were 2/3, your denominators would be 0, throughout this problem. And if a denominator is ever 0, well, then your expression is undefined, right? You're dividing by 0, and that's bad. But for any other value of s, go ahead and check it. Replace s with 0, with a half, with 3/4, whatever, 500, whatever you want, as long as it's not 2/3. And the value of the original expression should be exactly the same as the value of s plus 5. Right. And I'll leave it to you to check a few values if you wish. Alright, example 7. So same deal. Right, we're given the sum of two fractions that already have the same denominator. They both have this denominator of w squared minus 16. So I put them together, that common denominator will stay the denominator of the sum. So I've got w squared minus 16 in the denominator. And the numerator of the sum is, again, just the combination of the numerators of these fractions we're adding. So it'll be 2w squared plus 8w. Right, and this is great. Here's the sum of those two fractions. But now we try to simplify it because I see that the numerator and denominator can be factored further. Numerator, 2w squared plus 8w. I could pull a 2w out of that common factor for both those terms, and then what's left over would be w plus 4. Right, and then in the denominator, w squared minus 16, that's a difference of squares, w squared minus 4 squared. So that'll factor to w minus 4 times w plus 4. And then I'm hoping again you're seeing the common factor here. The numerator and denominator have a common factor of w plus 4. So I'll cancel those, and I'm left with the factors of 2w in the numerator and just w minus 4. And since it's the only factor left, there's no need to put parentheses around it, right? W minus 4 in the denominator. All right, and then once again, as with every other example, off to the side, I'll put some values that w can't be. Right. Well, going through this, I'm seeing, in the denominator here, there was a factor of w minus 4 and w plus 4. So w can't be positive 4, because that'll make w minus 4 0. It can't be negative 4 either, because that would make that factor of w plus 4 equal 0. I don't care that it get canceled out. Right? You may have seen, I did a video before where we were simplifying fractions. Remember, usually I did this before canceling. Right? Wrote down the values that can't be used for the variables. But just make sure that you don't use any values that make the denominators 0 anywhere. You don't want a denominator of 0 at any point throughout the problem. So you see how positive 4 would make all these denominators 0, negative 4 would make all these denominators 0. So those are no good. But for any other value of w, the value of the original expression should be the same as the value of this expression I ended with. And you can test that out. Replace w with 0, with 1, with 15, with negative 2/3, right? As long as you're not replacing w with 4 or negative 4, the value of the original should be the same as the value of the final. Alright, same thing, a very similar problem for 8. Both fractions we're adding have the denominator x squared minus 9. So when I add, that common denominator, right, x squared minus 9, is going to be the denominator of the sum. And then I combine the numerators to make the numerator of the sum. So 7x squared plus 21x. Alright, and that's great. There's the sum of those two fractions, but as I've been saying, we're asked to also simplify this. So after adding, after subtracting, simplify if you can, which we can here, right? The numerator can be factored. That would factor to 7x times x plus 3. And then the denominator is another difference of squares, x squared minus 3 squared, so that would factor to x minus 3 times x plus 3. And then I see the common factor of x plus 3 in both the numerator and denominator, so those will become 1, and those will divide out to be 1. And I'm left with, in the numerator, the factors of 7 and x, and in the denominator, the only factor left is x minus 3, so since it's the only one, right, no need for parentheses. You could put parentheses around it, that wouldn't be a problem, but there's no need for them. Alright, so that's as simple as that gets. Now again, off to the side, looking throughout the entire problem, I see that x cannot be positive 3 or negative 3. Right, because if x were either one of these numbers, you'd have a denominator of 0, right, throughout the entire problem. Except at the end, when x is negative 3, that's fine, but positive 3 would be bad. Right? But just because negative 3 is good at the end doesn't mean it's good throughout the whole problem. Right? I want to plug in numbers that are good throughout the entire problem, right, that don't make me divide by 0 ever. So as long as you plug in a value of x that's not 3 or negative 3, the value of the original sum should be the same value as this expression at the end. And I leave it to you to test that, test for different values of x. Okay, so examples 1 through 8, we were doing addition. adding two fractions that already had a common denominator. Right? For examples 9 through 16, we're doing subtraction. Okay, and don't forget the rule, right? I wrote it up earlier. If you have a over c and you subtract b over c, right? If the two fractions you are subtracting have the same denominator already, that denominator will be the denominator of the difference, and the numerator of the difference will be the first numerator minus the second numerator, a minus b. I know I had this rule written up after, during example 1, but I just wanted to write it up again right here. Now this is, you gotta be it's a little trickier this time, because when we do subtraction of the second numerator, when we do a minus b, if the second numerator, right, if this b has multiple terms, you're going to be subtracting that entire numerator. So subtracting every single term, not just the first one. So we'll have to do some distributing if the second numerator has multiple terms, and we'll see that come up in later examples. Alright, so same deal. Got a fraction minus another fraction. These two fractions already have the same denominator, 3a minus 7. So when I put I can put them, that means I can put these together, take the difference, and that 3a minus 7, that common denominator, will be the denominator of the difference. 3a minus 7 in the denominator there. And then I take the first numerator, right, 9a squared, minus the second numerator, 49, and this only has one term, right, this second numerator, so there's no need for parentheses around it. Okay, great. There's the fraction resulting in the difference of these two fractions right here. But right, just like I said before, once we add or subtract, then we simplify. Right? Now, the numerator is a difference of squares. This is 3a times 3a minus, and then this is 7 times 7. Right? So that'll factor to 3a minus 7 times 3a plus 7. So those are the factors of the numerator, and the only factor in the denominator is 3a minus 7, and I'm hoping that you can see the common factor of 3a minus 7 in the numerator and denominator. So I'm going to scratch those out, make those into 1. And all I'm left with is 3a plus 7 in the numerator, divided by 1 in the denominator. So just 3a plus 7. And then after, I'll state the values I can't replace a with. Alright, look throughout the entire problem. Whatever values of a ever make a denominator equal 0, those are bad. I can't use those. And that would be 7/3. Alright, a can't be 7/3, because that would make me divide by 0 throughout this problem. But a can be any other number I want. Alright, and test it out. Replace a with any number besides 7/3, and take this subtraction. Subtract these two here and see what number you get, and then plug it in the final expression, see what number you get, and they should be the same value. Alright, so because it's a new one with subtraction, I'll at least do one more of these where we test it out. Alright. So let's test this. And I got the value of the original difference, the value of the final expression, right, 3a plus 7. Now how about if a were 0? Well, this would be 0, right? 0 divided by negative 7 would be 0, minus 49 divided by negative 7. Well, 49 divided by negative 7 would be negative 7, but then we have minus that, so it'd be positive 7, the value of the original. And look at the final expression. 3 times 0 plus 7 would also be 7. Right? The value of the original expression is exactly the same as the value of the final expression. I'll do one more. Right? If a were 1, right, again, as long as we're not using 7/3, we're fine. We'd have 9 divided by negative 4 minus 49 divided by negative 4. So there's a common denominator of negative 4. 9 minus 49 would be negative 40. You have negative 40 divided by negative 4 would be positive 10 for the value of the original difference. Well, when a is 1, look at the final expression. 3 times 1 is 3 plus 7 is positive 10 again. You have 10 equals 10, same thing. And you could do this all day long. Right? Replace a with any value you want, as long as it's not 7/3, and the value of the original expression should be exactly the same as the value of the final expression, right, if you did everything correctly. All right, number 10. All right, pretty similar. Once again, as in all the examples in this video, we're subtracting two fractions with the same denominator. So that common denominator will go in the difference, right, 5b minus 6. And the numerator of the difference is, the difference of these numerators. First numerator, 25b squared, minus, and then again, the second numerator only has one term, right, 36, so there's no need for parentheses around that. You're only subtracting a single term, not multiple terms. Great, and there's the difference, this single fraction. Now, as in example 9, once we add or subtract, then we simplify. So we factor the numerator. Now the numerator is once again a difference of squares. That would factor to be 5b minus 6 times 5b plus 6. Right? And the denominator doesn't factor any further, so 5b minus 6 would be its only factor. And then it's obvious now that 5b minus 6, right, is a common factor in the numerator and denominator, so I'll cross those out, make those into 1, and I'm left with 5b plus 6 in the numerator and 1 in the denominator, right? So just 5b plus 6. Now again, the original expression and this expression will be equal for every value of b except 1, and that would be 6/5. Right? B cannot be equal to 6/5. Because if I replace b with 6/5, that would make these denominators 0 throughout the problem, and you can't do that, right? That's undefined. But any other value is fine. And I leave it to you to test some. Right? Replace b with any value you want, as long as it's not 6/5, and the value of the original expression should be the same exact value as the final expression. All right. So now we're getting into the trickier problems. All right, example 11. Do you see in the second fraction how the numerator has multiple terms? See, it has two terms, 21m and negative 30. So when we subtract, right, we're subtracting that entire numerator, not just the first term. So let me show you what I mean. All right, so we're subtracting two fractions. They have the same denominator already. So that's going to be the denominator of the difference, right? So 6m minus 30 is the denominator of the difference. And then when I do the numerators, right, we take the first numerator, 3m squared, and you're subtracting, again, you're subtracting not just 21m, but you're subtracting all of the second numerator. So the quantity, 21m minus 30. And people very often tend to forget this. They'll just put minus 21m and then minus 30. They'll just write the whole thing as it was. You're subtracting the entire numerator, not just the first term. I hope that's clear. So what we're going to have to do here, when we're subtracting something with multiple terms, you're going to be distributing the negative, right? Subtracting every single term of that expression. All right. So that'll add one more step here. So in the numerator of this new fraction, we have 3m squared minus 21m, right, minus that first term, but also minus negative 30, which will be plus 30. Right. Okay, I hope that's clear. Right. When you're subtracting an expression with multiple terms, right, you're subtracting every single term, distributing the negative. And then we still have that common denominator of 6m minus 30. Right. Great. So here's the difference, right? This fraction is the difference in these two fractions. It's just not simplified, that's all. So the numerator, there's a common factor of 3 in all three of these terms. I'll pull that out. And when I pull 3 out, you'd have m squared minus 7m plus 10. You know what? I'll do every step of this first one. So we have m squared minus 7m plus 10 left over, and that'll factor further. Same with the denominator. There's a common factor of 6, which is 2 times 3, right? So I pull 6 out, or 2 times 3, right? That's 6, but I factored it to 2 times 3. And then when I pull 6 out, the remaining factor is m minus 5. And I'm seeing some common factors right now, right? So I'll just cancel them as we go. And there's a common factor of 3 in the numerator and denominator, so let's get rid of those. And the numerator factors even further, right? M squared minus 7m plus 10, that would factor to m minus 5 times m minus 2. Right, divided by, and then since I already canceled the 3's, the factors of the denominator are 2 and the quantity m minus 5. And I'm seeing one more common factor in the numerator and denominator, and that's the m minus 5, right? M minus 5 is common. So I'll cancel those. And then finally I'm left with only one factor in the numerator, m minus 2, over, or divided by, and then only one factor left in the denominator, right? Just the 2. And there you go. Once again, though, the value of the original expression will be exactly the same as the value of this expression for any value of m except 5. Right? M cannot be 5. It can be anything else, but if you replaced m with 5, you'd have denominators of 0 throughout this entire problem, and you do not want that. Right? Dividing by 0 is an undefined operation. And again, I leave it to you to test. Plug in values of m and see if the value of the original expression is the same as the value at the end, and it should be, again, for any value of m except 5. Alright, and then 12 is very similar. See how the fraction we're subtracting, the numerator has multiple terms. So you're going to be subtracting both terms, not just the first term. I'll be distributing a negative, right? So I'll write that again here. So again, we're subtracting two fractions that already have the same denominator, right? This 4n minus 32. So that will be the denominator of the difference. Then the numerator is, I'm combining the numerators. We have 2n squared, right, the first numerator, minus the entire second numerator, minus the quantity 18n minus 16. Right, you're subtracting both terms, not just the first term. So again, we'll be distributing the negative to both of these, subtracting both terms from that second numerator. So that gives me this. You have 2n squared, then minus 18n, minus negative 16 would be plus 16. So there's the numerator after I subtract, take the first numerator minus the second one, get this. the denominator is still this common denominator 4n minus 32. Alright, so there's the difference in those two fractions. Great. But now we're asked to also, simplify, factor the numerator, factor the denominator completely. Alright, so this one I'm going to skip a few steps. I'll just talk it out loud here. There's a common factor of 2 in the terms of the numerator, so I pull out a 2, and what would be left over would be n squared minus 9n plus 8, which would factor to n minus 8 times n minus 1. Right, so I'm just skipping the step where I write the quadratic. Then the denominator, 4n minus 32, they have a common factor of those terms of 4. So that's 2 squared, right? 2 times 2, or 2 squared. So I pull 4 out, or 2 squared, and then what would be left over would be n minus 8. And now we can cancel some common factors, right? There's a factor of 2 in the numerator. There are 2 factors of 2, right? 2 squared in the denominator. So only one of those is going to go away. So that's why I'm going to make this 2 to the first power. And then you have a common factor of n minus 8 in the numerator and denominator as well. And that's it. So what I'm left with is, just the factor of n minus 1 in the numerator divided by, and then the only thing left in the denominator is the factor of 2. And there we go. And off to the side here, I will state the values I can't replace n with. And it looks like the only value I can't replace n with would be 8. So n can be any number you wish, except 8, right? Because if I replace n with 8, the denominators throughout this problem will be 0, and that's not good. That's undefined. And I leave it to you to test. Plug in any value of n you wish, as long as it's not 8, and check to see if the value of the original expression is the same as the value at the end of the final expression. And they should be if you did everything correctly. All right, next. So again, we're sticking with examples. All right, we're sticking with examples where we're subtracting a fraction that has multiple terms in the numerator. So again, that means we're subtracting all those terms, not just the first one. All right, so once again, as with every other example in this video, we're subtracting two fractions that have the same denominator, right? They have a common denominator. So that denominator is going to be the denominator of the difference. So p squared plus 4p minus 5. And I'm subtracting the numerators. Now, and really you're just combining like terms. So I'm going to do something pretty quickly here. I'm going to shortcut it. First numerator has a 6p squared minus 5p squared. That's 1p squared. I'm just combining like terms. First numerator has 3p minus 1p. 3p minus 1p. Remember, you're distributing the negative here. So 3p minus 1p is plus 2p. And the first numerator has a constant 4 minus the constant 7. 4 minus 7 is negative 3. So there's what I would get if I took the first numerator minus the entire second numerator and distributed the negative. I just kind of skipped ahead to what it would be after combining like terms. Hopefully that made sense. So there's our difference. But, as with all the other problems, I need to simplify this if I can. Now the numerator factors to p plus 3 times p minus 1, right? Those are the two factors in the numerator. And the denominator factors to p plus 5 times p minus 1. Okay, and then I'm seeing a common factor here of p minus 1. And so what I end up with is p plus 3 in the numerator divided by p plus 5 in the denominator. There's your simplified version of this difference. So the value of the original expression will be equal to the value of this final expression for every value of p except the following. P cannot be replaced with -5 or with +1. All right, because this p squared plus 4p minus 5 was a denominator throughout, and then we said that factored to p plus 5 times p minus 1. So if p were -5, you'd have a denominator of 0 throughout, and if p were +1, you'd also have this denominator of 0 throughout the problem, and that's not good. I don't want that, right? So I can, and I leave it to you. Check it out, test it out. Replace p's with any value you wish, except for -5 or 1, and the value of the original expression should be the same as the value of the final expression. All right, similarly for number 14, once again, you're subtracting fractions where the denominators are already common. The denominators are already the same. So the denominator of the difference will be that common denominator, q squared plus 6q plus 8. And you're subtracting the numerators. You take the first numerator minus the whole second numerator, right? So that means I'm distributing the negative here. You're subtracting every single term of that second numerator. And I'm just going to skip ahead to what we'll get. We have 5q squared after combining like terms. We'll have 5q squared minus 4q squared. That's 1q squared. 3q minus 9q be -6q. Then -9 minus 7 would be -16. Alright, so this is what I get after taking the first numerator minus every term of the second numerator, right, after distributing the negative and combining like terms. So wonderful. This fraction here is the difference between these two. Right? We just have to simplify again. Right? So factoring the numerator, that would factor to q minus 8 times q plus 2. The denominator would factor to q plus 4 times q plus 2. And we can see right now that the value of q can't be -4 or -2. So I'll put that up to the side already. Because if q were -4, you'd be dividing by 0. If q were -2, you'd be dividing by 0. You'd have a denominator of 0 throughout the problem, and that's bad. And then I see the common factors. Q plus 2 is a common factor of the numerator and denominator, so I'll get rid of those. And I'm left with q minus 8 in the numerator divided by q plus 4 in the denominator. Right? That's it. That's as simple as that'll get. And once again, test it out. Check out some different values of q, as long as you're not replacing q with -4 or -2. So replace q with 0, with 1, with 5, with whatever you want, as long as it's not -4 or -2. And the value of the original expression should be exactly the same as the value of this final expression. Alright, so now we're getting to our last page, and it's the same procedure. Subtracting fractions and then simplifying. And all these fractions have the same denominator. So both these fractions had this denominator of r squared minus 49. We're subtracting, right? So that common denominator will also be the denominator of the difference, r squared minus 49. And then as I did in the last problem, you're taking this first numerator minus the entirety of the second numerator. So we'll be distributing the negative. Right, subtracting every single term from that second numerator. So you got 5r squared minus 4r squared be 1r squared. 7r minus 5r positive 2r. And then -33 minus 30 be negative 63. Okay, so there's our difference, but we're also trying to simplify this. Right? So the numerator would factor to r plus 9 times r minus 7, and the denominator difference of squares would factor to r minus 7 times r plus 7. And even before I simplify, I'll point out that r can't be 7 or negative 7. Right? Because if r is either 7 or negative 7, you'll have a 0 denominator, and that's not good. That's undefined. Can't divide by 0. And now I'll cancel the common factors. I'm seeing the common factor of r minus 7 in both the numerator and denominator, leaving me with r plus 9 in the numerator, divided by, and then r plus 7 in the denominator. And once again, I leave it to you to check, test some values, see if you believe this. If you did everything correctly, you could replace r with any number except 7 or negative 7, and the value of the original expression will be exactly the same as the value of this final expression, r plus 9, then divided by r plus 7. All right, and one final example, very similar to 15, example 16. Again, we're subtracting fractions that have the same denominator. And if you're adding or subtracting fractions with the same denominator, that denominator will be the denominator of the final result, right? The denominator of the sum or the difference. So t squared minus 25 stays the denominator here. And then as before, we're combining the numerators. I take the first numerator minus the entire second numerator. So you're not just subtracting the first term, you're subtracting all the terms of the second numerator. So it's like distributing the negative here. And then we combine like terms, we'd get the following. 7t squared minus 6t squared be 1t squared. Then negative t minus 12t be negative 13t. Then negative 4 minus negative 44. So that's negative 4 plus 44, right? Remember, minus a negative is plus. Negative 4 plus 44 would be positive 36. Oops, sorry, not positive 36. Negative 4 plus 44 would be positive 40. All right, this is 44 minus 4. Sorry about that. So positive 40. So numerator is now t squared minus 13t plus 40 divided by, and then the denominator was that common denominator throughout, t squared minus 25. All right, so there's our difference. Great. But once again, after taking the sum or the difference, we must now try to simplify the fraction if it's possible. The numerator would factor to t minus 8 times t minus 5. The denominator, t squared minus 25, would factor to t minus 5 times t plus 5. And even before I cancel, I can tell you right now, the values of t I can't use. All right, hopefully it's obvious that I can't use 5 for t. I can't replace t with negative 5 either, because either way, replace t with 5 or replace t with negative 5, you're getting a denominator of 0 throughout this problem, and you can't divide by 0. And now I'll do some canceling of common factors. There's t minus 5 in the numerator, t minus 5 in the denominator, so those are canceled. Those become 1. And in the numerator, I'm left with t minus 8. In the denominator, I'm left with t plus 5. And there you go. And as in all the problems before this, I'll tell you, you can test this out. Plug in any value of t you want except for 5 or negative 5, and the value of the original difference should be exactly the same as the value of this final expression. All right, I'll leave it to you to test some values of t if you want to check that. Great. So again, pretty simple video, I feel, pretty simple problems because the denominators were already the same, right? So all we had to do was add, combine the numerators, add or subtract, and then factor the numerator, factor the denominator, and cancel any common factors. All right, so it wasn't so bad. You just had to remember how to factor some things, right? And I'm assuming again that you know how to factor polynomials. Please brush up on that if you don't. All right. So hopefully watching me go through these 16 examples helps you when you're working on problems similar to this. And thank you very much for watching.